All right, welcome everyone, and thank you for attending today's CGD seminar. Before we get started, I'll remind everyone of our CGD code of conduct at these seminars, where we offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. I'll ask that everyone please keep themselves muted throughout the seminar and hold any questions until the end, unless you have a burning clarification question. With that said, it's my pleasure to introduce today's speaker. Yana Silvy is a PhD student at Sorbonne University at Lausanne IPSL in Paris. Prior to that, she received undergraduate and graduate degrees in math and physics and a water, air, pollution, and energy specialization master's degree at ENSTA Paris. Her research interests include detecting human-induced temperature and salinity changes in the ocean interior and understanding the physical and dynamical processes causing those changes. Her talk title today is Processes and Timescales of Anthropogenic Heat Emergence in the Ocean. So with that, Yana, feel free to share your screen and take it away.
Thank you. Can you see my slides?
Yes. Okay,
great. Share screen. All right, thank you very much, Dan, and thank you all for having me. So I'm currently finishing actually my PhD at l'Océan in Paris. I'm submitting my manuscript in 2 days. And so today I'll be talking to you about the second part of my PhD work that I've been doing with my two advisors, Jean-Baptiste Salé and Eric Gilliardi, and with other colleagues at l'Océan here. So as you all know, the ocean has been warming, and we've been able to observe that upper ocean warming for several decades now from in situ observations of the ocean. So this is ocean heat content anomaly in the upper 2,000 meters of the ocean from 3 observation-based estimates. And this warming is projected to continue in the future. And so this is a figure from the AR6 that was published last August, and we can see that ocean warming is projected to continue in all of the 21st century scenarios in CMIP6 models. But the warming has not been uniform, and so here we show the observed warming rate in the upper 2,000 meters of the ocean. And you can see that some regions have been warming faster than others, and some regions have even cooled. So the CMIP models reproduce some of these patterns of change, with some regions that are warming faster and some regions that are even cooling. And in the future decades, this intensification of the warming is projected, and with particularly high storage of heat in the subpolar North Atlantic and north of the ACC in the Southern Ocean. So we are going to try to understand why this storage of heat is the way it is, and on which time scales it appears. So temperature anomalies are often decomposed into 2 components. So first, the direct heat flux anomalies are advected by the circulation, and this is referred to as the passive or added warming. Or indirectly, we have air sea flux anomalies in the heat flux, the freshwater flux, or the wind stress that are changing the circulation. And these changes in the ocean circulation are acting to redistribute the pre-existing temperature field. And this component is referred to as the redistributed warming, but it's depending on the sign of the change, it can also cause cooling. So quite a number of studies in the past couple decades have investigated this decomposition into passive or redistributive warming using, for example, passive tracers. And they've also looked at the role of individual surface fluxes. But almost all of these studies have looked at the long-term response or the equilibrium response under idealized forcing. So for instance, you might know the FAFMIP protocol. So FAFMIP is the flux anomaly forced MIP, and it is designed to study the ocean response to different surface flux perturbations. but the perturbations don't vary year to year. And so what we're going to be interested in here is to understand the respective importance of these different mechanisms and the respective role of individual surface fluxes under historical and future radiative forcings and compared to an internal variability. So really looking at the transient rather than the equilibrium response. So our framework of analysis is the IPSL large ensemble. So IPSL CM6A-LR is the version of the coupled model developed here at IPSL that has been used for CMIP6. It has 32 historical members, and these 32 members have been extended to 2059 under the SSP 245 scenario. And then for the remaining of the 21st century, there are about 11 members. So we really have a large ensemble from 1850 to 2059. So these historical members are initialized from a long PI control run. So here I'm showing globally averaged sea surface temperature. So the gray dotted line represents 2,000 years of PI control. And here it's the same for an AMOC time series. So 2,000 years of PI control, and each solid colored line represents a historical member. And you can see that it is branched from a different point in time in the PI control. And so this allows to sample different phases of internal variability. So it's called micro-initialization. And the particularity of this coupled model is that it has large low-frequency variability. And you can really see that from the AMOC and the PI control with this bicentennial mode of variability. And this is described in the paper by Waimin Zhang. And so these different historical members really sample this low frequency variability. And so averaging across these members, so here I'm showing the historical ensemble on the historical period. Averaging across these members allows to isolate the force signal, and we can see the clear surface warming here, and here a clear decline in the AMOC in the 21st century. So this model also has a deep ocean cooling drift below 2,000 meters. And so we have removed that drift for the analyses presented here. So now I show the warming patterns in the IPSL large ensemble. So this is the ensemble mean ocean heat content anomaly, so a vertically integrated ocean heat content, and zonal mean temperature anomaly. And it's the anomaly in the mid 21st century relative to 1850, 1899. So again, you can see that some parts of the ocean are warming faster, or at least have larger uptake of heat than others, and some regions are even cooling. Now, if I divide this anomaly, this ensemble mean anomaly by the intermember spread, intermember standard deviation, I obtain an estimate of signal to noise ratio. So this time we're not just looking at warming, but at warming relative to local internal variability. And so we can see different patterns emerging now with very large signal to noise ratios in the mode and intermediate waters of the Southern Ocean. And these waters have been actually already found to be hotspots of anthropogenic warming, and pretty large as well signal to noise ratio in the deeper ocean. So we're going to try to investigate why that is. And another way to look at this is instead of looking at signal to noise ratio in the 21st century, we're going to look at when the signal to noise ratio crosses a certain threshold. So we're going to look at when signal to noise ratio, for instance, here remains above 3. And so this is an estimate of what we call time of emergence. And so here we're showing the years. So the dark red colors mean the signal to noise ratio has crossed 3 before the 1980s. And the lighter colors mean it's crossed this threshold later in time. And the gray color means it hasn't emerged at all. And again, we can see that actually the earliest emergence of this warming is in the deep ocean, in the export pathway of Antarctic bottom waters. And we can see as well some early emergence in the mode and intermediate waters and in the ventilation pathways of the ocean. And so the goal here is going to be try to understand the processes that are driving these changes and their timescales of emergence in the framework of this coupled model and using the tool that is the large ensemble.
Yeah, we had a quick clarification question. Can you tell us the resolution of the ocean component of the model?
So it's Orca 1. So it's the horizontal resolution is about 1 degree, and it's refined to 1/3 of a degree at the equator, I think, and it has 75 vertical levels. I'm actually presenting the ocean model. The ocean model is NEMO 3.6.
Thank you.
In the IPSL coupled model. So to answer these questions, we've designed numerical simulations in the spirit of the FAFMIP protocol and of other studies, but here we're really targeting they're really targeted to study the transient response and to reproduce the response of the large ensemble and then try to decompose the total response. So we force the ocean-only component, NEMO 3.6, with fixed fluxes from the coupled model. So first we have a control experiment, which we force with 3-hourly surface fluxes from a coupled PI control. And so we do that to simulate the period 1850 to 2100. So we force with the different components of the heat flux, of the wind stress, of the freshwater flux at a very high frequency. And because we have these high frequency fluxes, our ocean-only control reproduces very well the mean state and the intra-annual variations of the coupled PI control. And I'll show you a few diagnostics just after this. And then in the same configuration, I just add to these surface fluxes a forced perturbation at monthly frequency that I just calculate from the historical ensemble mean. And it's just the anomaly relative to 1850, 1899. And so I basically take this anomaly and apply it on each surface flux. So the heat flux, the wind stress, and the freshwater flux. So now my whole experiment reproduces, has the internal variability from the control, which has itself inherited it from the coupled PI control, and the forced components from the large ensemble. And because of that, the whole experiment is sort of like an additional member to the large ensemble. And the only difference is that its internal variability from the PI control hasn't seen the influence of the external forcings. But this doesn't seem to affect this member very much, and it stays pretty well within the spread of the large ensemble. And again, I'll show you that just in a few seconds. And then we have sensitivity experiments in which we impose the monthly perturbation on each surface flux at a time. So only the heat flux or the freshwater flux or the wind stress alone, and then on both buoyancy fluxes together. And so now all of my ocean-only experiments are all phased together in terms of internal variability because they all have the background fluxes from the PI control, and they have the external forcings on different components of the surface fluxes. So to show you a few time series and validation of these experiments, here I'm showing in blue time series in the coupled PI control and in black in the ocean-only control. So this is global mean ocean temperature. So as you can see here, I have not removed the drift, and there is a small cooling drift, which I have removed afterward. This is global mean sea surface temperature. And these are two circulation diagnostics. So this is a diagnostic for the overturning cell in the Southern Ocean, in the deep cell. And this is a diagnostic for the AMOC. And you can see that our ocean-only control reproduces really well the interannual variations from the PI control. in the AMOC, we're missing some of the peak values, but overall, it's doing a pretty good job at reproducing the coupled model. So now I look at my whole experiment, which has the external forcings from the large ensemble. And if we look at, so it's changing over time, but if we look at the intra-annual variations, we can see that it's pretty phased in with the control. For global mean SST and for these different overturning diagnostics of the circulation. And to check whether the whole experiment is within the spread of the ensemble, I plot the historical extended ensemble. So there are 30 members, and this is the ensemble mean, and then all of the members are in this spread. And you can see that for all of these time series, my whole experiment is well within the spread of the large ensemble. But it has its own internal variability because it has its own initial conditions. All right, so with these different experiments, we can decompose the total response into individual surface fluxes. But I also want to investigate the response of the passive and redistributive components. And to do that, we do something that has been pretty much done in the community, and we implement a passive tracer. So this is often referred to as added heat, so T prime A. So our T prime A is initialized at 0 everywhere in the ocean. It represents an anomaly, and it is forced at the surface by the heat flux perturbation Q prime, just like temperature. But it's transported passively by the circulation in each of these experiments. So it doesn't affect density. And the thing is that we can do that in each of our experiments. And the only difference, it's going to be forced the same way in all of the experiments. And the only difference is that the circulation changes between these experiments. And so we can decompose the total temperature response in the whole experiment now into an added component, T prime A, my passive tracer, and a redistributed component by just making the difference between the temperature change and the passive tracer. And because we've implemented that passive tracer also in the control experiment, we can further decompose the added heat into what is called passive heat to apply the same terminology as FAFMIP. This is the equivalent of FAF passive heat. So it's the tracer in the control experiment. So it's been transported by the unchanged circulation. And then we have what we call nonlinear added heat. And it's the difference between the tracer in the whole experiment and in the control experiment. So it's the effect of circulation changes on this added heat. So to investigate the transient response of ocean warming in the ocean, we've decided to look at a few key regions that are important for the ventilation of the ocean. So here in the colors, you can see the age of the water masses. So it's a passive tracer that's implemented, and it's actually a CMIP6 output. And it shows you how ventilated different regions of the ocean are. So the light colors mean the water is new, so it's very well ventilated, and the dark colors mean it hasn't been ventilated in a while. And so we're going to look at 4 regions, 2 regions that are associated with upper ocean ventilation. So there are the subantarctic mode waters and Antarctic intermediate waters in the Southern Ocean, and the North Atlantic subtropical mode waters in the North Atlantic. And 2 other regions that are associated with deep convection and export of deep and abyssal waters. So the North Atlantic deep waters in the North Atlantic, and the export of Antarctic bottom waters in the Southern Ocean. And I'm employing the term water mass, but these boxes are actually fixed in space. And the idea is just to have simple diagnostics that are climatologically associated with the ventilation of these water masses. And we're going to see how temperature evolves in these different boxes.
Yana, we had another quick clarification. Can you tell us how TA prime is forced in the control?
So it's forced, let me see if I can go back. Sure. So in the control, it's forced by the Q prime. It's forced by the Q prime in all of these experiments. Even so in the control, there's no Q prime in the physics. So the temperature, the active temperature doesn't see Q prime, but my passive tracer sees Q prime and is passively advected in the ocean. So it doesn't affect the physics. It's just a fake way of inputting heat and then passively transporting it. I hope that's I hope that's clear.
Answered it for me. Thank you.
All right, so we're going to look at each of these boxes and try to decompose the different drivers and look at the timescales of the change. So first, we're going to look at subantarctic mode waters. So here I'm showing a temperature anomaly in this region over time. And so the orange is the temperature anomaly in the large ensemble, and the gray is the spread of the temperature in the ensemble. So it's a way to have a noise envelope, and it corresponds very well to interannual standard deviation in a PI control, for instance. So it's a way to represent the noise. And then the dark red line is the temperature anomaly in my OL experiment, and it's the anomaly relative to the control, which means it's a very good way of looking at the forced change, because we're removing the influence of internal variability, which is phased between the OL experiment and the control. So you can see that the OL experiment is well within the spread of the ensemble, and it actually follows pretty well the ensemble mean, which is not the case in every region. So if I look at the time when the OL experiment reaches a signal-to-noise ratio of 2, actually, if we look at the ensemble in the large ensemble, the spread of this threshold is pretty large, and this is because in the 20th century we're warming, but we're warming slowly, and so initial conditions have a lot of importance, and internal variability is pretty good at modulating the emergence of the force response in each member. And the more we go, the later we go in time, and the faster we warm, and so the more reduced the spread in the large ensemble is. So this corresponds to a signal-to-noise ratio of 5, and now to a signal-to-noise ratio of 7. And you can see that the spread, so here the double arrow represents the spread on the horizontal of the ensemble anomaly. And so you can see that the spread is reduced, and the force this means the warming has emerged in more and more members at the same time. So now we want to decompose this response into different mechanisms. So here I'm adding the heat experiment in the light red, and you can't see it very well because it's actually very well superimposed on the OL experiment. So this suggests the heat flux perturbation alone causes all of the warming that we see in this region. And actually it hides the fact that there's a balance between a cooling by the freshwater flux. So this is the temperature response in the water experiment. And here it's the temperature response in the wind stress experiment. So what's occurring in these different experiments? There's an increase in the westerly winds in the Southern Ocean. So this is causing more northward heat transport across the ACC, and so more subduction of heat in these mode waters. This is something that has been documented before. And here we find actually that in this model, this warming mostly occurs over the 21st century. And when you look at the time when the signal starts to emerge from internal variability, actually the wind, the effect of the wind hasn't had time to really delay the emergence. And this is pretty new because it seems that the effect of the increased westerly winds actually play a strong role, at least in the ventilation of the region. But in terms of temperature response, it doesn't play a strong role for the emergence of the signal itself. Now, the cooling in the water experiment, we explained by the fact that there's increasing precipitation at high latitudes. So that this causes freshening at the surface. And because high latitude waters are cooler in the surface than in the subsurface, there's a cooling. We're stratifying the surface and cooling the surface. And this cooling is transported northward and subducted north of the ACC. But actually, these two mechanisms compensate each other, and you can see that the heat and you can see that the whole experiment is superimposed on the heat experiment. Now, the other decomposition that we can make is to look at our passive tracer. So this is the dotted line. So this is T prime A in the whole experiment. So you can see that it's always slightly larger than the total temperature anomaly. And it starts actually fairly early in the 20th century. And so the difference between the dotted line and the solid line is the redistribution. And we can see that there's a small redistributed cooling that is actually attributed to the heat flux experiment itself, which is acting to stratify the surface and so prevent a little bit of the added heat from reaching the subsurface. And so this we can see that by looking at the added heat in the heat experiment itself. And there's no really difference between the T prime A in control and T prime A in all. So just to sum up for this region, we've seen that it's dominated by the storage, the passive storage of heat. That circulation changes delay the emergence by only by about 10 years. If you look at the difference between the dotted line and the full line at the time when the signal emerges, so by the turn of the century, there's only about a 10-year delay. And total warming has emerged by the early 21st century. So now if we turn to the North Atlantic subtropical mode waters, we're going to look at the same decompositions. So here we have our warming in the large ensemble and in the whole experiment. This warming emerges a little bit later than for the Southern Ocean. And again, we see the same thing with large spread in the ensemble because of this slow 20th century warming, and the spread is reduced over the 21st century. In the heat experiment, the subsurface warms more rapidly than in the whole experiment. And when we look at the other experiments, we can see that this is due to some cooling caused by the wind stress and not so much by the freshwater flux. And here I can answer a few questions about that, but there are some nonlinearities in these experiments. And you can see that the buoyancy experiment is actually superimposed on the heat experiment. So this cooling by the freshwater is not seen in the buoyancy experiment. And so now if we look at the added warming, we can see that it's really large, and so there is a strong redistributive cooling, but this cooling occurs actually just over the 21st century. And again, if we look at the time when the signal starts to emerge from internal variability, this redistributive cooling hasn't had time to have much effect. Even though at the end of the 21st century, it's very strong, and it's important to take that into account for the total amplitude of the warming. And to look at how this redistributive cooling occurs, you can see that the wind stress experiment, the cooling in the wind stress experiment doesn't explain all this redistributive cooling. And if we look at the added heat in the heat experiment and compare that to the temperature anomaly in the heat experiment, we can see that almost all of this redistributive cooling comes from the heat flux experiment itself. And so we can explain that. So this is consistent with a few things, either with AMOC weakening that is causing less transport of heat northward, but also by the fact that the heat flux brings heat, but it also brings more stratification of the ocean, which means the heat is prevented from being transported transported in the interior of the ocean. So in 2100, we can see that the total warming is caused by a large added heat as well as redistributive cooling. But by the time the signal emerges, it's mostly added warming that's important, with only small impacts of circulation changes. So actually, we at the time of emergence, it's similar to the Southern Ocean, except that the effect of circulation changes occur later in time than in the Southern Ocean. Now, if we go deeper into the ocean, so we're looking at the export of Antarctic bottom waters, it's a whole other story here. We again have a strong warming that is actually occurring quite early in the 20th century and continuing in the 21st century. And again, we can see that if we look at the time when the signal-to-noise ratio crosses 2, it's very early. It's in the 1940s. But the spread is very large, and it's also very large in the early 21st century. The spread of the ensemble, and it only starts to reduce well into the 21st century. So you really have a lot of internal variability modulating the force signal in the ensemble members. If I look at the heat experiment, we're seeing warming, but we're not seeing warming that can explain the total response. And now I plot the temperature response in the water experiment, and now we see some drastic warming in the 21st century. And so we're going to try to explain why that occurs. I'll just finish plotting my different ocean-only experiments. So the buoyancy experiment adds up the warming from the freshwater flux and the heat flux, and has stronger warming than the total response. And it's partly counterbalanced by a cooling caused by the wind stress. And it's occurring over the 21st century. And now when we look at the added heat alone, we can see that it starts to increase over the 20th century, but it pauses over the 21st century. And actually, added heat in the control experiment is much larger than in the OL experiment. So this is the nonlinear component. So I'll try to explain what's happening. So at the surface in the subpolar Southern Ocean, we see a strong increase in the buoyancy fluxes. So this is the freshwater flux anomaly in buoyancy, the contribution to the buoyancy flux from the freshwater flux and from the heat flux anomaly. And we can see that they're both increasing, but the freshwater is actually more important than the heat flux contribution to the buoyancy flux. And we can see that increase in buoyancy in the freshwater flux is causing a shutdown in deep convection. So we're bringing freshwater at the surface, which means we're stratifying the surface. And because of this stratification, we have a decrease in deep convection. And the opposite is occurring for the wind stress. So we're increasing the winds and we're increasing vertical mixing. And so we have deeper mixed layers. And because the buoyancy fluxes are acting to increase stratification, we actually have surface cooling, as I said before, but strong subsurface warming. And this is what we see here. This is the subsurface warming that is caused by the fact that we're decoupling the surface from the subsurface. And the winds in the wind stress, because we're increasing vertical mixing, the warmer subsurface waters can release more heat to the surface, and we see this cooling in the subsurface. And this is also consistent with the decrease in the Southern Ocean deep cell, the meridional overturning. And we can see that it decreases in the oil experiment. And this is due to a strong decrease led by the freshwater flux, the freshwater flux anomaly, and a little bit counteracted by the wind stress. So in this region, we have several processes acting together and on different timescales. So over the 20th century, we kind of have this 50-50 between the added heat component and the redistributive warming by the freshwater fluxes. But over the 21st century, the added heat remains quite small because we're decreasing the deep convection. We can't bring this excess heat in the subsurface. But the fact that we are decreasing the overturning warms the subsurface, and the wind stress, the increasing winds act to actually cool the subsurface. So we have all these processes either adding up or counteracting each other on these different timescales. All right, and just to finish with my different regions, now I'm switching to the North Atlantic deep waters. And we see some warming as well, but this time it actually occurs much later. And we only see that there's warming over the 21st century and a little bit, starting a little bit over the end of the 20th century. And the spread in the ensemble is really large. And we know that this region is associated with very large internal variability, large decadal variations as well. And there's also the fact that the forcing from aerosols over the 20th century has counteracted the forcing from greenhouse gases, which could explain the fact that we don't have much change over the 20th century, that is only starting to see that change over the 21st century. So now if I look at the response to the heat flux perturbation, we actually don't see a lot of change. And we'll see that this is due to the two components counteracting each other. And the warming is actually caused a little bit by the freshwater flux perturbation, as we saw before in the Southern Ocean. And the wind stress is not causing much change. So now if we look at the added component, we actually see some strong added warming, and this is coherent with the fact that there's deep convection in this region, and so it's very easy to bring heat downwards. But there's also strong redistributive cooling, and we can see that in the added heat in the heat experiment. So all of this added heat is added heat is actually counteracted by a redistributive cooling caused by the AMOC weakening, and I'll show you a few diagnostics. If circulation hadn't changed, so T'(A) in the control experiment, we would have had much more added heat in this region because we're actually slowing down the circulation as well. So let's look at the mechanisms. So over the subpolar North Atlantic, we have an increase in the heat flux, and we have an increase in the heat flux that is very important compared to the increase in the freshwater flux. So this increase in the heat flux is actually causing a decrease in deep convection in the subpolar North Atlantic. And so here, this is the mixed layer depth. And you can see that in all the experiments that include the heat flux perturbation, mixed layer depth shows. And this is coherent with the AMOC weakening that we can see here, that is again driven by the heat flux perturbation. So this AMOC weakening is cooling the subsurface and is also acting to, because we don't have as much deep convection as when the circulation had not changed, we're not bringing as much added heat in the subsurface. So in this region, by 2100, we have a total warming that is caused by a strong added heat counterbalanced by a strong redistributive cooling caused by the heat flux perturbation, and a residual redistributive warming by the freshwater flux. And the warming is delayed to the 21st century, and this is, I think, consistent with aerosol forcing in the Northern Hemisphere. So now I'll try to sum up what's going on in these different regions of the ocean. So in the upper ocean ventilation pathways, we have seen that the emergence of the warming from internal variability is driven by the uptake of excess heat that is passively transported in the ocean. And there's only a small delay by circulation changes. And even though circulation changes might be important to set the amplitude of the warming later in time, by the time for the emergence of the signal from internal variability, they don't play such an important role. In the subsurface subpolar Southern Ocean, we have seen that there is an overturning slowdown caused by the buoyancy fluxes that is countered by an acceleration in the overturning caused by the wind stress. And so overall, we have a small added heat it's small because the overturning slowdown prevents it from penetrating in the subsurface. So a way to see this is that if you think, how does the ocean uptake anthropogenic heat? You'd think, okay, it uptakes it where there's deep convection, because it's very easy to mix the waters and to make this heat penetrate in the ocean interior. But actually, this overturning circulation is slowed down. So the excess heat is only small, and it is the slowdown itself that is warming the subsurface, because the subsurface waters are naturally warmer than the very cool surface, and they're prevented from releasing their heat to the atmosphere because we have increased stratification at the surface. And in the North Atlantic, we also have a slowdown in the circulation, but this time the slowdown in the circulation acts to cool the subsurface versus the added heat that naturally enters the ocean. And the emergence of the signal, of the warming signal in the North Atlantic, is delayed compared to the Southern Hemisphere, which is consistent with aerosol forcing acting in the late 20th century. So to conclude, we've developed a framework to reproduce the ocean's response of the IPSL CM6 model with an ocean-only model. This framework does a pretty good job at separating internal variability from external forcing in ocean-only simulations. And we've been able to do that because we've forced the ocean with very high frequency surface fluxes to reproduce internal variability from a PI control. And we've isolated the external response from the ensemble mean. The warming patterns in the ocean were decomposed into different contributions using sensitivity experiments and passive tracers. And as we saw just before, we found very different mechanisms and timescales to explain the penetration of anthropogenic heat in the ocean, depending on the ventilation pathways. And sometimes these mechanisms are actually counterintuitive and act on very different timescales. So I'll stop there. Thank you very much for your attention.
Excellent. Thanks a lot, Yana, for sharing your exciting work. We now have ample time for questions, so I'd encourage people to go ahead and raise your hand, or feel free to enter questions in the chat, and I'm happy to read them out loud. All right. Peter has a hand raised. Go ahead, Peter.
Hi, thank you for a nice talk.
Hello.
In the deep Southern Ocean, your plot that was reducing the strength of the overturning, the reduction was on the order of 7 or 8 sphedrams. So what is the value of that overturning circulation in the control coupled experiment?
Right. I might have, so I think it's on the order of wait, just so you're talking about this plot.
Yes, this bottom right here.
Yes, I think it's of the order of a dozen of Sverdrup, but I can check. Actually, I don't want to say. I know that it's about. I think it's about that. I think it's about a dozen or 15 Sverdrup. Is that what you had in mind?
Yeah, I'm thinking that's a little strong compared to.
Yeah, I'm sorry, I don't have the exact number because I've been looking at anomalies mostly, but yeah, I have made that plot. I can, maybe I can find it, but I'm not sure.
Yeah, it would be nice to see the mean overturning circulation from the control coupled experiment.
Yeah. So I can probably dig that up, but I'm not sure I can find it right on the spot. Sorry. Because
the warming signal emerges in this location really surprisingly early,
yes,
1940 or 50. So I'm wondering whether that is because the mean overturning circulation is quite large compared to most models. And then this reduction of the mixed layer depth really cuts it off, that overturning off very early on.
So yeah, so I think I'm not confident about what happens here in terms of timescales. I mean, especially when you think about the how coupled models reproduce the Southern Ocean mechanisms in the Southern Ocean. There are lots of, like, deep convection is mostly done in the open ocean, and that's very rare in the real ocean. And this is why, so I think we can mostly learn from the balance of mechanisms rather than the timescales for what concerns the Southern Ocean. And because deep convection mostly occurs in the open ocean, and there's too much deep convection in the open ocean, when we increase the stratification, it shuts down really fast. And this is what's occurring over the 21st century. We can see that really clearly in the buoyancy forced experiments. But it doesn't explain why there's a slowdown in the circulation as early as the 20th century. And this is something that I still haven't figured out, because I can't see clearly what's causing this slowdown just from the mixed layer depth. And it could be that the circulation is so sensitive to small changes that right away we're seeing this subsurface warming. But the deep convection shutdown only occurs at the end of the 20th century. So I'm not sure what are really the mechanisms that are driving this early 20th century changes. And it could be sensitivity in the circulation. I'm not sure, but I should check how this model compares to other models in terms of this deep overturning cell. Yeah.
Excellent, thank you. We have a question in the chat from John Liu, who asks, for the case of NEDW, slide 15, why is the TA prime in the control so large?
So I think it's large because if you look at the AMOC, it shuts down in the so we have an AMOC shutdown in the perturbed experiment, and you can see also that the mixed layer shows in the perturbed experiment, but in the control, deep convection continues to happen, right? So in terms of passive warming, when you think about inputting heat at the surface and then transporting it in the ocean, when there's deeper convection is going to be more, it's going to be just, the added heat is going to penetrate the subsurface ocean more effectively when there's deep convection than when there's a decrease in deep convection. So that's how I explain the fact that added heat is much larger in the control than in the perturbed experiments. And that's actually also the case in the Southern Ocean. If we go back, here the T prime A in control is also larger than the T prime A in the old experiment.
Excellent, thank you. I had a question about so it seems like the signal to noise ratio is highly dependent on the representation of internal variability in the model. I was wondering if you thought that that could be sensitive to the choice of a 1 degree model, or if maybe that's not so important on the timescales that you're looking at.
That's a hard question. So I really I don't know how resolution could impact the signal to noise ratio. I haven't worked with high resolution models. It would definitely be interesting because you would resolve more in terms of eddies. You would resolve more mechanisms. I'm not sure how that would impact interannual variability. I guess we have to try to before answering that question, but I think to me it was also interesting to see that the spread across members reproduces very well. The spread across members at any time reproduces very well the interannual variability from the PI control. Like if you take the standard deviation of the PI control, it gives you the intermember spread because we have enough members to do that. I don't know how resolution would change that. So I think it would be pretty interesting to look at that in other models, but I'm not sure that higher resolution models have these number of members. I don't know if you're aware of large ensembles that have a better resolution than 1 degree in the ocean, at least.
I'm not, but maybe a good reason to run some. Peter has a hand again, I believe.
Is it okay if I ask another question?
It's permitted.
So you have these emergence times that sometimes say the heat increase should have emerged by, say, 2015, especially in the upper ocean 2 regions. I was wondering whether that has occurred in the observational data sets that you referenced early on in the talk.
Yeah, so I'm not sure about the North Atlantic, but in the southern, this region, the Southern Ocean, mode and intermediate waters. So there have been, they were, I think the first, I'm not sure if they were the first, but Helen Hewitt, Banks at the time, and Jonathan Gregory really looked at these water masses in the early 2000s, and they compared the early coupled models with observations, and they already said that these water masses were hotspots of anthropogenic signal to detect the anthropogenic signal. And more recently, there was a paper by Neil Swartz et al. In 2018 that ran detection attribution analysis with the CANISM2 large ensemble, and they detected the warming and the salinity, the temperature and the salinity changes in this in the Southern Ocean. In the, I think it was between 30 degrees and 60 degrees south, so more like the mid latitudes. And they detected anthropogenic an anthropogenic signal in these water masses in the observations using the fingerprint from their model. So yes, it's been verified at least in the upper ocean in this region. And I think there was a CMIP5 detection and attribution analysis more recently by Will Hobbs in a 2021 paper, and they also detect the anthropogenic influence in the observations using the CMIP5 fingerprints. And they also look at deeper water masses, but there's more uncertainty concerning the deeper ocean because there are less observations. So yes, the Southern Ocean mid-latitudes have been really looked at in terms of detecting anthropogenic change in the ocean. And because it's really in terms of the background circulation, it's a conduit for the ventilation of the ocean. And I guess it's what explains the fact that we can detect change so early because we have changes at the surface, and these changes are just subducted along the background circulation very easily.
Thank you. I just wanted to make a comment that I really liked the set of experiments that you did, the 7 experiments with the ocean-only model, and then the way you analyzed what was causing what. I thought that was very nice.
Thank you very much.
Steve Yeager has a hand raised. Go ahead, Steve.
Yeah, thanks, Yana. That was really nice. My question was a follow-up on this signal to noise ratio. I guess it's a signal to total variance ratio. And obviously the denominator plays a role in modulating that ratio. And you can see it on this slide. You can see it on the AABW slide as well, if you go back to that. The spread has quite a bit of variability to it. So, you know, that signal that emerges around 1940 is associated with a decrease in ensemble spread. So it could be associated with that decrease in noise in the ensemble, which might be related to how the ensemble is responding to external forcing. So I'm curious if you've looked at how the ensemble spread varies as a function of time and whether that plays a big role in time of emergence in your analysis.
So I've also run the time of emergence analysis using the PI control noise, and it doesn't change that much because actually, I mean, if you look at, so the gray actually shows you the denominator, the intermember spread. And so it changes in time, but it stays at the same order of magnitude, right? And it's it's mostly in the North Atlantic that we can see that it diminishes, but with the PI control noise that doesn't change in time, we have about the same timescales of emergence. Why? Because the signal is not varying that much. I think that's why, because if there was more variability within the signal itself, you would probably go back within, you know, the envelope of noise and then go up again. And here it's so clear that the warming, even though it may be slow at the beginning, it's not. I think what's more where there's more uncertainty or sensitivity is on the which threshold you choose. Is it 2 signal to noise? Is it a signal to noise ratio greater than 2 or greater than 3? And because the 20th century warming is so slow, that causes large differences and large spread in the ensemble. But I'm not sure. I mean, I'm not sure the fact that the noise itself is changing in time is causing. I mean, I'm not sure that on the first order that's what changes these timescales of emergence.
Just to clarify, then, this orange error bar here, is that from the full large ensemble? That was my. Yes,
it's the full large ensemble, but for the temperature anomaly. So this is why it's so low in the beginning, because it's the anomaly relative to the first 50 years, and the gray is the spread in the temperature, the absolute temperature.
Okay.
Because I didn't want the noise to depend on the baseline. I mean, I think that makes more sense, but I mean, and you can really see how it evolves. And I think it's in the North Atlantic, and here you can really see that that weakening, and that may cause some earlier detection. But again, it's on the same order of magnitude, so I'm not sure that it plays such an important role. At least when I compute the time of emergence on a map using PI control or using intermember noise, doesn't really change the patterns that we see.
Thank you.
Excellent. Well, we're at the top of the hour, so I apologize. I'll ask you to follow up with Yana over email. Thanks again, Yana, for sharing your exciting work with us. And everyone, I'll look forward to seeing you at the next talk. Take care.
Thank you, Dan. Thank you, everyone.